University speak about this amazing automated conjecturing mathematics, very appropriate to this seminar. Everybody who will be here and behave and not use a smartphone is invited to come to dinner right after the talk at the usual place, 6:45 at Evelyn's. But I need to know, let me know, I'll be standing here right after the talk and be taking names.
All right, thanks everybody for coming. Thanks Doron for the invitation. Nico is my collaborator on this code. He comes out of a group that's at Ghent University in Belgium. The department is Applied Mathematics and Computer Science, and most of what the department does is graph generation or other kind of object generation. They have a pure math department, and the pure math department is more than half finite geometries, crazily enough. Anyway, so I'm going to talk about two problems that we've been working on. This, the big idea here is automated mathematical discovery. There's lots of pieces. There's been lots of work on automated theorem proving since the 50s, WZ theory. The piece that we're working on is you start with an object type and an invariant here. An invariant means a number associated with that object type, and you want a theory in some sense of that invariant. So I'm a graph theorist. Most of the examples that I've worked on are for graphs. The independence number is an NP-complete graph invariant. So you won't find, say, a polynomial time formula for the independence number of a graph. But maybe the theory here would be upper and lower bounds for the independence number. Maybe you could keep improving that theory. Other object types include matrices, and then a determinant would be an associated matrix invariant for square matrices. Integers would be an object type. Maybe the number of ways you could represent the integer as a sum of two primes might be an interesting number associated with an integer, an even integer. Well, you could define this for any integer, but the even integers are a special case. Doron's written a bunch of papers on chomp, and our very first project on playing with this code, we did some stuff with chomp positions. A number of cookies would be or some sort of a game with cookies on the board. I'll show you a picture later. But the number of cookies would be a chomp invariant, some number associated. And intersecting set systems might be another kind of object type. For finite intersecting set systems, the number of elements of the family would be an associated number. And the other kind of problem that we are interested in is given an object type and some property, some Boolean of those objects that you're interested in a theory to investigate. So here a theory, the very best thing would be some polynomial time characterization, but maybe you won't get that. So maybe you could get some sufficient conditions, or maybe you could get some necessary conditions. So again, graphs, matrices, integers, and chomp positions are kinds of mathematical objects. Here, associated properties for graphs, an associated property would be whether or not it has a Hamiltonian cycle. For a matrix, matrix property would be whether or not it's totally unimodular. For an integer, maybe you're investigating primality. And for chomp positions, you might want to know whether they're, in some sense, winning positions. Okay? So those are the kinds of problems that we've been working on. And the purpose of the talk is to tell you about some experiments we've made, some code that's on GitHub and is freely available, and to maybe entice you to play with the code or get your students to play with the code and come up with some interesting conjectures. It's going to be a conjecturing program that I tell you about. All right, so I'm a graph theorist. The two main examples I'm going to talk about in this talk are related to the independence number of this graph theoretic invariant. There's a couple of people that think smart people that think P is equal to NP. Goldilocks thinks P equals NP. Maybe about the same time that Doron visited VCU, Neil Robertson also visited and told me that he thought P equals NP. So maybe there is a polynomial formula for this.
He was kidding as well.
He wasn't. He actually got mad at me. I said, Neil, you've never written anything about this. And he told me I've worked on this problem every day of my professional career. And then he sketched a proof. He had some complexity levels, and he told me that if I understood the proof of the graph minus theorem, all the levels would collapse in the same way. The proof is still on my board. He was serious. So one of my goals in life now is to figure out this proof. Yeah. And for Hamiltonicity, this is another hard problem. Maybe. So I'll talk about some getting some necessary and sufficient conditions. All right. So what do humans do if we're investigating, say, the independence number of a graph? Well, one thing you might do is look up the literature and see what the theorems are. You might try and find some examples where the theorems in the literature aren't giving you tight bounds, where there's lots of slack to investigate. You might try to come up with some new bounds on your own, and as you're doing your mathematical doodling, you might test your own conjectures about some familiar graphs. For sure, the Peterson graph, whatever your favorite graphs are, and those bounds are typically functions of numbers associated to graphs that you already know, but maybe you'll create some new ones in your investigations. And similarly, if you're investigating Hamiltonicity, you might start by looking at what's known. What are the known necessary and sufficient conditions? What are the known theorems of this type? What are the graphs that are Hamiltonian, that aren't touched by any of these theorems? And then you might formulate your own necessary condition, usually in terms of already existing properties, but maybe you'll make up your own along the way. So, for the students, the red vertices are a set of vertices in this graph that are pairwise non-adjacent. No lines between any of the red vertices. And you can't find 5 vertices that are independent. So the independence number of this graph is 4. We'll use alpha throughout the talk for the independence number. All right, so our program generates expressions that could be used for upper bounds, for instance, for the independence number, or lower bounds for the independence number. And here I've got some betas. Think of the beta 1, beta 2, beta 3 as already existing graph invariants. And then here, the square root and the plus, these are operations that you could use to combine the already existing graph invariants. So the square root is a unary operation that you could apply to any of the invariants. The plus is a binary operation that you can combine any 2 of the existing invariants. So ingredients to our program for any of the cases that we're talking about, you've got to first, does this have a laser on it?
Yes.
I'm worried about
The top.
the top.
No.
Okay,
Yeah.
so if I hit the middle?
Up.
Up.
There is. Wait.
I see it now.
There is a green.
Oh, I see it. Okay. What typically happens is, if I'm given something with buttons, I'll hit the button that turns everything off. So I wanted to ask first. Okay. So you tell the program some, say, graph invariants. Maybe we've got 40 operators in there now of unary and binary type. And then you can systematically generate the complexity 1 expressions are just the invariants themselves. The complexity 2 expressions will be any unary operator applied to any of the invariants. The complexity 3, so you see we've got labeled trees, so we're just forming all of the labeled trees. Our code actually produces 100 million labeled trees a second. Generating the expressions is not one of the hard parts here. Here's another complexity 2 unary operators applied to an invariant gives you a complexity 3. For things that you see in the literature that are of interest to humans, conjectures are usually never more than, say, complexity 10, something like this, but the program will keep on going until it satisfies certain stopping conditions that I'm talking about. All right, so the heuristic, the conjecture generating heuristics are actually from Graffiti. Graffiti was a program written by my master's advisor, Shimon Feilovich. Originally in the 80s, the heuristics that he settled on are from the early 90s. So certainly generating expressions isn't enough. The first person that tried to write a conjecturing program was Hao Wang at IBM in the late 50s. And his program generated thousands of conjectures just by generating expressions, basically. And he didn't have a good way to filter these things. And he ended up with a printout, a huge stack of printout potential conjectures. Maybe there was some good stuff in there, but you somehow need to filter them. You can't take your stack and hand it to Doron and say, I think there's some good stuff in here. So for Graffiti, there's 2 heuristics, and one of the heuristics is Feilovich his program made conjectures for graphs. So essentially what we've done is take the ideas of Graffiti and generalize them to any kinds of objects. His ideas weren't graph specific, it's just the code that he had written was basically graph specific. Truth was one of his heuristics. The program would know some graphs, it would generate some potential upper bounds for the independence number, and then the program would check if that potential upper bound was actually true for the examples that he had told the program. So truth for examples. And the second heuristic is some kind of a significance heuristic. It requires that a new conjecture to be included in the list of conjectures tell you something new. So if you're generating upper bounds for the independence number, you have some number of graphs, and you have some already stored conjectured upper bounds, you'd want the new potential upper bound to be smaller in value for at least one graph than any of the other conjectured upper bounds. This would tell you something new. Here's a kind of a picture. So here I've got a schematic with 8 graphs, and I've got the independence number on the y-axis, and the dot represents the independence number for this graph, the independence number for this graph, and so on. And then I've got some lower bounds. So the maximum of your lower bounds is itself going to be a lower bound. So here's what this schematic says, is the maximum of the lower bounds actually equals the independence number for this graph. None of the lower bounds nor the upper bounds touches the true value of the independence number for this graph. So here we need better lower bound theory and better upper bound theory. So we have lots of room for improvement here and so on. Here the lower bound can't be improved. In each case here, at least one or the other can be improved. If ever you have the case where your lower bounds equal your upper bounds, then there's no more room for improvement. Stop. You have a formula. All right, so our program is called Conjecturing. It's going to make some conjectures. I'll show you examples. And for each of these conjectures, if it's true, presumably we can find a proof. And then you could, and I'll show you how, tell the program the theorem. And when you prove it, then you tell the program and add it to the program's theory, and then you let it make new conjectures.
The human proves it or the computer proves? So far, human.
Human, yeah, sure. I don't think there's the last interesting theorem that I saw a computer proof of was the Robbins conjecture in 1996. That is some open problem, not a toy problem that a human hadn't already solved. Have you seen anything more recently?
No, it's on WZ.
Oh, except for, yeah. Except for everything that comes out of WC. Robbins conjecture and everything from WC, yeah, sure.
So some of the conjectures that were made by this program were interesting conjectures that were proved with interesting proofs?
There were a couple, yeah, that I'll show you. There was the chomp one that you gave OEIS $100 for.
Yeah.
So that was, I call that a Zeilberger interesting problem.
Okay.
If the conjecture is false, then there should be a counterexample, and you can add that counterexample to the program. And the way that the program is designed, because it's got this truth heuristic, it can't remake the now falsified conjecture, because it's got to be true for the objects that you've told. All right, so for graph theory, the so one of my dreams is to code every graph that's ever shown up in a research paper. I call this, I did start to spend some amount of time doing this, and then it turns out to eat up a lot of time. It's kind of useful, but it's not the fun part of mathematics. It's like mathematical grunt work. I read recently, so there's this Large Hadron Collider that they spend $1 billion a year to maintain. And I thought, $1 billion? That would pay 10,000 mathematicians $100,000 a year. And if you think one of those 10,000 could code all the graphs that have ever been in a research paper, that would be a useful thing. I tell people about this $1 billion, and people think, oh, $1 billion. $1 billion here, $1 billion there. But when you tell them 10,000 mathematicians making $100,000, now it sounds like real money. Imagine all of the things that we could support with $1 billion. So we get a lot more than 112 invariants coded, and a lot more than 585 graphs.
But in principle, it should be a computer program that would do machine learning. Well,
in principle, yeah.
Okay.
But again, it couldn't be me that coded this because I don't know anything about this. But one of these guys making $100,000 should do this. One of the things that slowed the problem down is we have some big graphs and we have some NP hard to compute invariants. And the way that the raw version of the program runs, the version that I showed the students this afternoon, is all of the values are getting recomputed each time, and the program just builds a table of the graphs and the invariants. It fills in the table with values, and then it fills in all of these expressions. So each time it's recomputed. One thing that we did last summer is do some database work to build a database of all this stuff. It's an extra step to load the database, so I didn't show you this, but there are directions on the web for if you ever get to the point where you're running graph conjectures and you're wondering why the program isn't doing anything, it's because it's trying to compute some NP hard invariant on some too big graph, and you sit there and you wonder if anything's happening. It's really frustrating. So we coded the database. I mentioned this theory variable. What you'd, if you really want practical conjectures that are telling you something new, you want those conjectures to beat the existing theory in some sense. And for us, that means to give a better upper or lower bound for the invariant relations conjectures, or for the sufficiency conjectures. We want a conjecture that tells us something about one graph that the previous sufficiency conjectures didn't tell us. So the union of the existing conjectures plus this graph is bigger. For necessity conjectures, you want the intersection of the graphs that satisfy those necessity conjectures to be smaller. And so this is how we've coded these significance tests. And we can tell the program the things that we know and force the program to try and beat the existing theory. So here I say best lower bounds for independence. They're not best in any mathematically precise way. These are of the maybe 20 or 25 lower bounds for the independence number that I've coded. These are the ones that in practice have given me the best practical results. The point is there is some lower bound theory for the independence number of a graph, and we could tell the program about all of these lower bounds. These ones all happen to be efficiently computable, so that helps. 2 summers ago, so the last 5 summers, I've organized some sort of research project with basically anybody that's interested, undergrads. We've had some high school students, some grad students, some other faculty members, and we just hang out in a room like this and run conjectures and talk at the board. So 2 summers ago, we investigated bounds for the independence number of a graph. And I was telling Doron, one of the things that I do with students is not start with our whole database and everything that we know, and add examples one by one so that the students have an opportunity to find counterexamples and to construct and play. One of the first conjectures was this lower bound on the independence number, maximum degree minus the number of triangles. I've written a lot of words here for the proof, but the idea of the proof is easy. This is just a local condition. So it says find some vertex of maximum degree and figure out the local independence number. The global independence number has to be at least the local independence number. Nevertheless, I've collected lots of independence number bounds and hadn't seen this one before, and it was actually tight for some of our examples. And here's an interesting open lower bound conjecture. We couldn't prove it. We spent a lot of time trying to prove it. I eventually offered anybody $10, but $10 is $10 for me isn't the same as $10 from maybe Eric or something. $10 Larson conjectures probably not worth saving the check and putting it on your refrigerator. The interesting thing here is that this Lovász stated number, by the way, it's the 40th anniversary of the Lovász stated number. He defined this number as an upper bound for the Shannon capacity in the 1979 paper. It's an amazing number. It seems like it would be hard to compute. There's a bunch of equivalence definitions in a very nice paper by Knuth called the Sandwich Theorem. One of the definitions is a optimization over all orthogonal representations of the graph. So an orthogonal representation is where for every pair of non-adjacent vertices you're represented with vectors that are orthogonal. So you can always find a trivial orthogonal representation by taking the unit vectors in R of the order. Nevertheless, this number is actually can be approximated in polynomial time, and it's an upper bound of the independence number. It's a real number, so its floor is the upper bound of the independence independence number. And here we have the independence number as a function of something that's an upper bound for the independence number. So in some sense we've got, if this were true, we'd have independence number trapped between two polynomials. Well, if we have for any graph either the independence number would equal the floor of low oscillator or something more. So I think that's kind of neat.
So this conjecture was made by your program?
Yeah. Yeah.
And as far as you know, it's not false yet.
Not false. We've done quite a bit of testing on it. Yeah. So it's, I really wanted it to be true and worked hard at finding it, either proving it or finding a counterexample. And also we've collected a lot of upper bounds for the independence number from the literature. Again, these aren't best in any precise sense, but these are good ones in practice. And so we've coded these all as theory when we're doing our investigations for the upper bound of independence numbers. And the program made this interesting conjecture that the independence number is bounded above by some function of the radius. This one interested me because it's not in the literature, and the radius is a lower bound for the independence number. So again, we've got independence number trapped between two functions of something. And this one I knew was true because every graph has an induced radius critical graph of a certain form, and you just have some structure you can grab onto. You can write out the details, but the details are essentially recognizing that you have this certain kind of substructure, checking that it's true for the substructure, and expanding. And the programming of the conjecture.
So in this case, you could prove it, the conjecture. So the conjecture was made.
The conjecture was made by the computer.
And it was a new result.
And yeah.
And you could prove it.
Yeah.
And in hindsight, the proof was not that long.
The proof is not that long.
But not
it might have been longer if this wasn't already known. This was. Yeah. And here's an open upper bound conjecture that the program made. So this one says, an upper bound for the independence number of a graph is the average distance between any pair of distinct vertices raised to the sum of the degrees, so twice the number of edges. So this one seems like it's got to be true, but we don't know how to prove it, and we've done quite a bit of testing on it. And again, average distance is a known lower bound for the independence number of the graph. So again, we have independence number trapped between a function of something.
Do you have any examples where this is tight or anywhere close to being tight?
I don't have any off the top of my head, and it's generally not tight.
Oh, sure.
Yeah.
I believe that's that part of it.
Yeah.
I don't know if it's best possible.
No, I think it's a terrible, terrible bound, but I have no idea how to prove it. But when the program made the conjecture, it had to be better than whatever else the program knew for at least one graph. So it could be terrible for every graph and really good for one program. Okay. All right. So Hamilton's graph is Hamiltonian. If you could find a cycle that visits all of the vertices exactly once and comes back to the beginning. This is another NP-hard problem, determining whether or not a graph has a Hamiltonian cycle. There's not many necessary conditions in the literature. So Ron Gould at Emory has written three big surveys on graph Hamiltonicity, and maybe there's three necessary conditions in the these surveys. And I asked him once, why are there so many more sufficient conditions? And he said, well, almost every graph is Hamiltonian. So to get a necessary condition, you need a class of graphs that's bigger than the Hamiltonian graph. So it would also have to be almost every graph and more. So the graph can't have any cut vertices, is one. And there's also this curious Laplacian eigenvalues bound. So we know a couple. And this is food for the program. Here's a curiosity that the program made. The program conjectured if a graph is Hamiltonian, and if it's cubic, it's class 1. Class 1 here is Wiesing's theorem says that you can properly color the edges with either a number of colors, which is the maximum degree of the graph, or the maximum degree plus 1. And the class 1 graphs are the graphs that you can color with the maximum degree. And so the conjecture is equivalent to if a graph is Hamiltonian and cubic, then it's class 1. And when you write it like this, it's an exercise for students. Just take your cycle, it's cubic, so the only other edges have to be a matching. The graph being Hamiltonian and cubic forces you to have an even number of vertices, so that cycle around, you can 2 color, and then that matching, you can 1 color, that's it. So it's not a great necessary condition, but it's a new necessary condition. Now the sufficient conditions for Hamiltonian theory is a lot more rich. There's well-known theorems by Dirac and Bohr and Schwadl, various types, and we've coded a bunch of these. Again, for the purpose, we wanted to make conjectures that said something new, that said conditions that applied to at least one graph that weren't handled by any of these famous theorems. Here was, again, when we were playing, so this one I couldn't believe that the program made. In fact, I thought it was something was wrong with the program. Circular planar is outer planar. It's Sage's, for whatever reason, whoever coded this originally in Sage didn't use the more common word. I thought, so outer planar means not only can your graph be embedded in the plane without any edge crossings, but also all of those vertices can be put on the outer face. So you think, that's your Hamiltonian cycle right there. What's the 2 connected condition for? Then you go, oh, an outer planar graph can have a cut vertex. So then you don't have a Hamiltonian cycle. The 2 connected forces there not to be any cut vertices. So while the theorem is trivial, it was amusing. Here's a more interesting one. If a graph is planar and vertex transitive, so is planar transitive was actually not coded by us, it's built into Sage, then it's Hamiltonian. And so I first fed the conjecture to Ron Gould, survey writer, and Brian Alsbach, who's an expert on vertex transitive graphs, and they didn't know this result from the literature, and we proved it. So there's a new sufficient condition for a graph being Hamiltonian, and the proof wasn't hard, but it uses some ingredients. So vertex transitive graphs have to be regular. Type showed that 4 connected graphs are Hamiltonian, so you only have to worry about 2 connected and 3 connected cases. 2 connected, but not 3 connected is easy. So Mader has this theorem relating the degree of a regular graph to connectivity. So we only have to worry about the connectivity 3 case. This forces the degree to be 3 regular, or no more than 3.5, but it's enough. And then there's another theorem, and just connected the pieces. There was this infinite class of graphs to check these are, you've got a polygon on top and a polygon on the bottom, and paths between them that you can just cycle up and down and around, and it works. The program conjectured if a graph is bipartite and strongly regular, then it's Hamiltonian. It turns out you can prove that if a graph is bipartite and strongly regular, then it turns out to be a complete bipartite graph. So you're going to be forced to have the same number of vertices on the top and the bottom, vertices on each side with every vertex across. So you can see that that would be Hamiltonian, but it was conjectured by the program. And here's one conjecture that we could improve, mostly because we have no feeling for distance regularity. There is some literature on distance regular graphs, but none of us can prove it, and we have passed this one around. It's still open. So it's program made this after we proved bipartite and strongly regular. Then we told it that theorem, and it came back with this conjecture. It said, I've got at least one graph that this would be an improvement. Well, the cube is.
So what is this regular?
A graph is distance regular if it's regular, and for any pair of vertices at that distance, I'm thinking of so distance transitive is something related. I can tell you distance transitive, but I don't remember the definition here. Sorry about that.
So this is still open, is fine?
Yes. All right, so I've been giving you graph theory examples, but again, the program is general. You just need to tell the program some examples of objects. You need to code up some numbers or some properties for that object type. You need to tell the program some invariant, like independence number or property, like Hamilton's E-line bounds for, and then whether you want upper or lower bounds or necessary or sufficient conditions. You could tell any theory that you want. And so long as you can code examples of the object types, you can get going and play. So some of you, I showed an example of using the program. The program is written as a Sage package. This screenshot is from, there's a web interface for Sage that makes the program easier to use for and more intuitive for students, less hacky looking. So you tell the program, here on the top you've got some list of graphs, current graph objects. You've got some list of properties. Here I've got these properties. I'm not using that list of properties. I must have been using the list of properties that's from our database. Property of interest. So here it's Hamiltonicity. The theory. So here are the theorems that will tell you in the program that it's got to beat is if a graph is a cycle, then it's Hamiltonian. If it's a click, it's Hamiltonian. Or if it's theorem 1, so theorem 1 is a function that says it's a Boolean that tests whether a graph is bipartite and strongly regular. So it's got to produce conjectures that beat those three properties. And the default is to make sufficient conditions. So it's made some conjectures here. So if a graph is planar and regular, then it's Hamiltonian. That's the kind of thing that you get. This one's definitely false, but the students won't know this right away. And part of the fun for the students is figuring out what these conjectures are saying and finding counterexamples. When you get the counterexample, you can add it back to that list of graphs. Keep playing. But this is what it looks like. This is the call to the program. Right there, that's it. And I'll tell you a couple of more examples. So Chomp is a combinatorial perfect information game. I mentioned Doran's done a lot of analysis on what happens is you start on a full rectangle and the players alternate eating a cookie, and then in this version of the game you remove every cookie that's below or to the right. If you eat this cookie, you remove every cookie or below or to the right. And the program would just represent these as lists, 3, 2, 1, 1, 1. So it's a perfectly good mathematical object. And David Gale proves that the first player in a game of Chomp has a winning strategy. But
If you start with a rectangle.
yeah. If you start with a rectangle. But except for 1 or 2 row Chomp, nobody knows what that winning strategy is. Doran says that 3 row Chomp is the boundary between easy and impossible. So we generated conjectures for Chomp positions. P positions is where the previous player to play has a winning strategy. So after I make my move, Doran and I are playing Chomp, I want to make a move that is a P position. That I hand over to Doran as a P position. This is where if I've got a winning strategy, I can continue this winning strategy. So when I'm making a move, there's different things that you do, just like you're playing chess. You would think ahead, what are the possibilities? Or you could have a theory of P positions. One of the conjectures. So the objects that we used in this example were just boards that we had computed were P positions with some recursive map. So we had some database of P positions, and the program we defined a bunch of Chomp invariants. We just made stuff up. There's no theorems, or maybe not a lot of theorems, Chomp theorems of this type. And it's something you could do if you're playing with any kind of mathematical object. Make up your own numbers that are associated to that object and see what kind of conjectures you get. And one of the conjectures that the program made is for a P position, the number of cookies should be at least twice the number of non-empty columns minus 1. And there are actually, so the other kind of positions are n positions. There are n positions that satisfy this condition. So this is actually has some discriminatory power. So if I'm looking at my possible moves, if I see some possible move, that's going to give me a position that doesn't satisfy this conjecture. I shouldn't make that move. And that would be that the P positions all have satisfied this inequality. We proved it. Students. Here's something I alluded to earlier. You could define a function. This function, I made it up because I wanted to play with integers. So I wanted to play with what could the program do that might be interesting related to Goldbach's conjecture. Turns out that this function actually exists and by this name in the literature. So it's the number of ways that an integer can be written as a sum of 2 primes, and even integers. One of the conjectures that the program made was that, so digits 10 is the number of base 10 digits in a base 10 representation of an integer. So this one is trivially true, but it's always, since this guy's an integer, well, this will always be true, but for at least one integer, there was equality, and that's why it must have made this conjecture. Here's a more interesting one. This number of representations of an even integer as the sum of two primes is at least the number of base 10 digits of the integer minus 1. So this is a very strong conjecture. And it was true for everything that we tested it on. I kind of like it because Filovich, when I was his student...
This is like log base 10 effects.
Yeah.
So still very weak compared to what probably do.
Filovich always emphasized that stronger statements can be easier to prove than a weaker statement. Also easier to find counters.
But the first one is obvious, the first one, because that's the one.
Yep, well, so this one's true.
Conjecturally.
But the program did make it.
Yeah.
And this isn't my brilliance. And I wouldn't make this in math time and just take credit for it. The program made it. This is, I'm not a number theorist, but this is an example of the kind of thing that you could play with. I think I have 2 minutes to go. You could make conjectures for determinants. Here I made of symmetric matrices. And I just started defining matrix invariants. There are theorems like Hadamard's bound for the determinant. These kinds of things exist in the literature. And if you're interested in bounds for the determinants, so I know a couple of these theorems that I've used. It's not something that I've ever worked on. It's something you could generate and play with in the same way that we play with the graphs. All right, so here's my last example. So here's a non-mathematical example. I have 1 minute before Dawn kicks me out. What's the next term of the sequence? 18. But you're all mathematicians, so the next term, that would be the 6th term. You know that no matter what you want, you could put a million here and find a rule. In fact, a degree 5 polynomial that would give you any term. There is no correct answer here. Nevertheless, humans have a feeling that there should be that 18 should be right. And so you can define sequence invariants, and you can have the program make conjecture about what this term is in terms of the smaller subsequence, what this term is in terms of the smaller subsequence. And sequence invariants that you've defined, and you can get some conjectures. How about this one? What's the next term?
112.
112. I like the bold conjecture. The program claims that a lower bound for the sequence, it doesn't know that it could find a degree 3 polynomial that would make any answer right. It says the last term is at least this and less than or equal to this. These are the same. The program came up with a theory that the next term should be the average difference.
So it means we are trying to find our recurrent relation.
Say it again?
We are trying to find our recurrent relation.
No, I was just playing, actually. I know. But maybe that's how you describe what the program has done. And then I was trying to make a program that would guess the next term, so I just went from 1, 2, 3, and I had tested whether the number satisfied the theory. The first number that satisfies the theory as the next possible term was 112. It's kind of interesting. It's doing something, I don't know, human-like. There's maybe the last slide.
I can pass IQ test. IQ more than 90.
Yeah. What's the next term? Last one.
243.
Yeah. The program made these conjectures, and we see a lower bound and an upper bound that match. And then the way that I wrote the program is I just checked 1, 2, 3 until I found a number that was satisfied by this theory. And the program said 243 is the next number. So anything will work, but the program is intelligent in some way. All right. So this is our code for the conjecturing part of the program. All of this stuff we've coded for graphs is here. And if you play around with any of the stuff, I would love to correspond with you. And thanks again for the invitation. invitation.
It was a beautiful conjecturing talk. And Craig will be glad to answer questions in private, and everybody